So, continuing from last time, we have our feasible region, and remember that in the feasible region we need to pick out the vertices. The vertices are just the corners of each feasible region. In this case we have 4 vertices. The ordered pairs go on your left column in your table that you're going to use with your objective function, which is right there, and we rewrote it right there. We're going to insert these numbers into the objective function and come up with answers here. And then we'll use that information to answer the question, which point in the feasible region maximizes the objective function. So we're going to be looking for whatever ordered pair gives us the biggest number as a result. That will be the ordered pair that maximizes our objective function. So we have 0, 0. We have 0, 5 halves, which is not a guess. We know it's 5 halves from that right there. You cannot guess on these. Over here we have 3, 1, and then here we have 2, 0. So now we just substitute these numbers into our objective function to get our answers. So we plug 0 in. It'll be 2 times 0 plus 0. Well, that's just 0. We plug in the next ordered pair, 2 times 0 plus y, which is 5 halves. Well, that gives me 5 halves. And then 2 times 3 plus 1. 2 times 3 is 6. 6 plus 1 is 7. And then we have 2 times the x-coordinate, which is 2, plus 0, which gives me 4. So now that we have used the objective function with all of our vertices, we look to see that we are trying to maximize. So that means we're going to look for the biggest result that we got. The biggest result was this 7 right here, which means that this ordered pair right here maximizes the objective function. So the answer to this problem then is 3, 1. If it's not a story problem, your answer will be an ordered pair just like that. If it is a story problem, then you'll need to take this answer and go back to what those coordinates mean and then say, it'll take 3 squirrels and 2 kittens, or whatever it is, and actually write down what the answer means in terms of that problem. Okay? If it said what point in the feasible region minimizes, then we would look for the smallest value, and the smallest value here is this 0, which corresponds to the ordered pair 0, 0. So this one would be your minimum. This one is your maximum. If I asked you for the maximum value, then your answer would be that number right there, not the ordered pair. If I asked you for the minimum value, then your answer would be that number right there, not the ordered pair. Because they said what point in the feasible region, that means I need the ordered pair. Okay? Next problem, very similar. This is actually a pretty typical looking system of constraints, your system of inequalities sitting right here. How many inequalities are there? There are 5. This one right here is what? That is our, use the right vocab word. This is my objective function. This is the thing that's either going to be maximized or minimized. Which are we going to do in this problem? Maximum or minimum? Both. It says find the point that maximizes and the point that minimizes the function. So we're going to find both. No big deal. It's no extra math. We just have to realize that we're finding both. All right, to do this now, all we need to do is graph each one of these inequalities. There are 5 of them. Sometimes it helps to write them individually. So I have for sure x is less than or equal to 6. But what does this one say? X is greater than or equal to -2. I also have y is less than or equal to 5. And what's the other one? greater than or equal to 1, and then I also have this one, which thankfully is already in slope-intercept form, so I'm ready to graph that one. Okay, so we just graph these now. We have x is less than or equal to 6. That will be what kind of line? Vertical line going through 6. Again, for the 100th time, graph incredibly carefully. The more careful you are, the better, the easier time you're going to have with your vertices when you try to pick them out. Next up, x is greater than or equal to -2. Actually, before I do that, I need to figure out which way I'm going to shade. Less than means I'm going to the left, so I'm putting little arrows on here to the left. Okay, next inequality, x is greater than or equal to -2. That will be a vertical line, and I'm going to shade to the right. Good. Again, very, very carefully line that ruler up, shading to the right. So my constraints have already restricted me to this little region in between. The rest of my constraints will further restrict me down to a feasible region. Y is less than or equal to 5. This will be a horizontal line that goes through 5. 1, 2, 3, 4, 5 is right there. Very, very carefully. I need to recalibrate this thing. And we're shading which way? Below. Finally, y is, well, not finally, but finally for the stuff that I rewrote, y is greater than or equal to 1. That will be another horizontal line. This one's going through y equals 1. And we're shading above. So as of right now, before we put that last one in there, we're currently restricted to this region right here. And within that region, I already know all the vertices. These are all exactly at nice integer values. That's good to know. When I graph that last one, it's going to cut through this thing in some way, and it's going to create my actual final vertices. So I graph y is less than or equal to x plus 3. To do that, I go up to 3 on my y-intercept, and then a slope of 1. So I'll put in a bunch of dots so that I can have the most accurate graph possible. While I'm putting those dots in there, I see that I hit right there, and I hit right there, so I know for sure that those are going to be vertices in my feasible region. I still have to very carefully draw in that line. And this one says shade which way? It says less than or equal to. That's shade below. So I draw my arrows in. And now we were in that little rectangle. What is the shape that we're looking at now? It's that trapezoid. So I'm going to shade that in here. That's way too big. So there's our region right there. Maybe I should have used the highlighter. Doesn't matter. Okay. So now we need to pick out our vertices. I have a vertex here, 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 here. One thing I will say, you can't see the x-axis anymore here. But I'll see people make a mistake a lot of times. They'll see that x-axis and think that it's a boundary, or sorry, the y-axis, and think that it's a boundary. But actually, that constraint lets us come all the way over to here. So be careful. Make sure your axes aren't confusing you. We want to write down those ordered pairs. I'm just going to start at the tip right here. The coordinates there would be what? So for x comma y, I have -2 comma 1. My next one, this one, 2 comma 5, My next one, just keep going around. 6, 5. And my fourth one, 6, 1. I write my objective function, which was given to me right here. I rewrite that in my middle column. That is what I'm going to substitute those values in. And then I write my answers over here. So for my first ordered pair, what do I write? Okay? -5 times -2 would be 10 plus 2, 12. Next one, what do we write? Okay? What do we get? -10 plus 10 is 0. So I'm going to stop here, actually, and I want to point something out to you. If we were to guess, just by looking at this feasible region right here, which ordered pair gives us the maximum value, which ordered pair would you think? If you're trying to guess. Just by looking at the picture, a lot of people would say probably that one right there. And the minimum value probably, if you're looking at the picture, would seem like it's going to be that one right there. I'm going to tell you to never assume that. You can't tell from the picture which one is going to be a maximum, which one's going to be a minimum. A lot of times, it'll be the exact opposite of what you're thinking of. And a lot of the other times, it will be completely different than any of those. So don't assume anything. Keep going. We have -5 times 6 plus 2 times 5. What do we get? -20. And finally, we have -5 times 6 again, but plus 2 times 1. What do we get? -28. All right, so the problem asks us to find the point that maximizes and the point that minimizes. So what's the maximum here? The maximum value is 12. The ordered pair that gives us that maximum is -2, 1. So max equals 12, and that happens at -2, 1. That's the answer I would prefer to see. In the back of the book, it's just going to say -2, 1. But I'd like you to put it together so that you understand that the maximum value is 12, but the ordered pair that gives you that value is -2, 1. We also need the minimum. What's the minimum? -28 is the minimum. So we're going to write min equals -28 at the ordered pair 6, 1. So if I put those on my graph, I have -2, 1 is the max, and 6, 1 right here is the min. Never would have guessed that. We could take everybody in the entire school and ask them where they think the maximum and where they think the minimum is, and nobody would have guessed that. Not even the calculus kids. They know, but they would know enough to say, I don't know. You know what I mean? Like they could figure it out, but they would know to say, I'm not sure, just by looking at the graph. At least I hope they would. You know what Google is? Google it. Polk County. Doesn't really matter in the context of this problem. But you have at most 20 hours to make shirts. You want to spend no more than $600 on supplies. You want to have at least 50 items to sell. So these are your constraints. From this information, you will create a system of inequalities and then graph them, come up with a feasible region, generate a function to maximize or minimize. In this problem, it says how many t-shirts and how many sweatshirts should you make to maximize your profit. And it also says how much is that maximum profit. So picture us going through that problem. In the end, we'll have that table set up. We'll have a bunch of answers from all of those ordered pairs. We're looking for the biggest number. That will be the maximum profit. And then the ordered pair that gets us there will tell us how many t-shirts and how many sweatshirts we should make. So just the nature of that question right there alone tells me what my variables are. This is a story problem. You want to start with defining your variables. What are the two things that I am changing? The number of sweatshirts and the number of t-shirts. Okay? You read the problem carefully and you will automatically see what your variables have to be. Now we need to pick a couple letters. Pick letters that make sense. S and T, X and Y, L and M, whatever, okay? For this problem, S for sweatshirts, T for t-shirts makes sense to me. If I pick X and Y, yeah, it's going to get me, it'll get me solving the problem. But if I pick X and Y, I might not remember exactly which X is and which Y is. Of course, now that I said that, I'm going to change that to X and Y. No, I'm just kidding. I'm not going to. Okay, so now we have our variables. What do we do? The inequalities. Set up your inequalities. So just start looking at information. We have t-shirts and sweatshirts, blah, blah, blah. Don't know where Polk County is. Guess it doesn't matter. All right. On this page right here, it says, well, that's really hard to read for me. Can you guys read that on yours? What does it say? It takes 10 minutes to make. Supplies cost $4. And what else? Profit is $6. All that information is going to be necessary to make our system of inequalities, our constraints, and also to make our objective function. The objective function is going to ask us to maximize profit. So we want our objective function to be dealing with profit. Okay? So that's where we're going to come up with the profit, is from that little line right there. What about the three-color sweatshirt? What does that say? Take 30 minutes to make. Supplies are $20. Profit's $20. Okay. So now we're going to use that information to come up with our system of inequalities. Maybe you like the objective function first. Doesn't really matter. System of inequalities. We know we have at most 20 hours to make shirts. Okay? So hours. At most 20 hours. So whatever I do, I better not go over 20 hours. So now what I'm going to do is I'm going to go through and try to find where I'm spending hours. So on my information here, it says takes 10 minutes to make. Here it says takes 30 minutes to make. Okay. So that's time, right? But this is hours, and they're giving me information in minutes. All minutes? That's reasonable. The other choice would be all hours. Okay? One way or the other. So instead of 20 hours, let me erase that 20 hours and turn that into minutes. How many minutes are in 20 hours? 3 minutes? 1,200? 300. I got 20 hours. There's 60 minutes in an hour. So that would be 1,200 minutes. I have 1,200 minutes to use. And for the blue t-shirt, well, S and T, so S comma T, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T. So S comes before T, so I'm going to write S first. So for the sweatshirts, it takes 30 minutes to make a sweatshirt. So that's 30S plus, it takes 10 minutes to make a t-shirt. So 10T has to be less than or equal to 1,200. I can't spend more. I have at most 20 hours to make shirts. So whatever I do, I better not go over 20 hours, which means less than or equal to. You want to spend no more than $600 on supplies. So again, notice this was minutes, minutes, minutes. Now the next line down, it says you want to spend no more than $600 on supplies. No more than. That is less than or equal to as well, and that's $600. So now that I have money going on here, I want to talk about money. This is supplies. So over here, supplies cost $4 for the blue t-shirt and $20 for the sweatshirt. So I'm going to write what? 20S plus 4T has to be less than or equal to 600. So again, this is $20, $4, $600. It's all money here. It's so money, it doesn't even know. You guys have no idea what that's from. Nothing. Nothing just happened. You want to have at least 50 items to sell. You want to have at least 50 items to sell. At least 50. At least is this guy 50, and we're talking about items now. That's right. S plus T has to be greater than or equal to 50. We're not done. We have used that information. We have used that information. We have used that information. In order to get there, we had to use that information. We used that information. We use that information, we use that information. We're not done with the system of inequalities. The two trivial ones, we can't make a negative amount of shirts. T has to be greater than or equal to 0. S has to be greater than or equal to 0. Those are obvious, but it helps to put those down as well. So you're probably selling it for $40. Yeah. Okay, now the last thing. So this is the system of inequalities that we're going to graph. The last thing to write is the function that we're going to use to optimize the situation. The function is going to come from profit. We're trying to maximize profit. So that's where the information has to come to make our function. F of my two variables, S comma T, equals. That's a function in terms of S and T. The profit for the sweatshirt is $20. So I make $20 per sweatshirt that I make. 20S. The profit for the t-shirts is it 6? So 6T. Okay, so from this situation right here, you have now created the constraints and the model so you can figure out, if this was you trying to make money here, which situation will give you the best chance to make the most amount of money.